In this video, I'm going to talk to you about the Wronskian. So let's say that we had a problem where we were trying to decide that several functions form a linearly independent set or not. And I'm not just talking about polynomials. We saw how to do that with polynomials. But imagine that I had, a logarithm, an exponential, a trig function, etc. How would we show that? Well, as I pointed out in the notes, you could use some identities to see if they were linearly independent or not. But you'd have to have some functions that were very specific. The example in the notes was sine squared x and cosine squared x. Obviously, those add up to 1. So if you pair those with a third constant function, then those would be linearly dependent. But again, if I have a wide variety of types of functions, that can be much more difficult. So to determine if they're linearly independent or not, what we do is we compute the Wronskian. So suppose that we have n functions, let's say f1, f2, up to fn. What I'm going to form is a determinant. It's going to be an n by n determinant. And what I'll do is the entries along the first row are going to be those n functions. And now how to fill out the rest of the Wronskian. In each column, I'm going to do successive derivatives of that function until I have n entries here. Now, because the first entry in a column is going to be the function, I'm actually going to have n minus 1 derivatives below that. So in this first column, I'll have f1 prime, f1 double prime, etc., down to f1, its n minus first derivative. And I would do the same thing for f2, and so forth, all the way to here at the end. All right. And so now what I want to see is about the Wronskian. If I want to determine if they're linearly independent or not, what I will do is I will compute this determinant. And if that determinant is 0, and I don't just mean could equal 0, I mean that it is 0 all the time. If it is not 0, then the set forms a linearly independent set. If it is 0, then they are linearly dependent. So let me show you that through 2 examples. On this first one, we have a function that's just x, and we have a function that's sine of x. So when I compute the Wronskian, it's going to be a 2 by 2 determinant. I'm going to put x and sine of x along the top row. And now what I need to do is I need to compute the derivatives of these. So the derivative of x is 1, and the derivative of sine of x is cosine of x. And now when I compute the determinant, I'm going to get x cosine of x minus sine of x. And clearly that is not the identically the 0 function. Are there x values that make this 0? Yes, x equals 0 is one of those. But this is not just the 0 function all the time. And so therefore, because this is not 0, these are linearly independent. All right, let me show you one that's a little bit more difficult, and that would be this one right here. So this one's going to be a 3 by 3, and I will have 1 e to the x and e to the 2x right here. So I need to do all the derivatives of those below, 2 derivatives in total. So, of course, 1's derivative is 0, and then that derivative will be 0 as well. For e to the x, it's going to be e to the x on all of them. And here, I'll use chain rule. I'll get 2 e to the 2x, and then I'll get 4 e to the 2x. So when I compute this derivative, in fact, I can expand along, or not derivative, excuse me, the determinant. When I expand along that one right there, what I'll get is 1 times, and it'll be positive 1, of course, times this. So when I compute this derivative, I get 4e to the 3x minus 2e to the 3x. And that's equal to 2e to the 3x, which of course is not the zero function. So therefore, the set is linearly independent. Hopefully that makes sense. If you have any questions, let me know.